Thank you, Andrew. Good afternoon, ladies and gentlemen. I'm really honored and privileged to share with you the vision of the future of the energy infrastructure for our nations, for North America. And in a nutshell, we want to make the system smarter, more resilient, more secure, and sustainable. That's what I'm going to share with you in the next 17 minutes. The main part of this that I will begin is what have we learned in the last 14, 15 years working in this area, and what are the underpinnings of understanding complex lifeline infrastructure systems, not just power grid, but how do these infrastructures hang together? What are the ways that we can make them more secure, more resilient, and integrate intermittent sources, dynamic sources of storage, of generation, demand into them? In a sense, enable smart, adaptive, complex infrastructure. So to begin with, I share with you some of the background. This is the work that I had the privilege of doing when I was at Washington University in St. Louis. What you're seeing here is an F-15 aircraft that an Israeli pilot landed with a missing wing. This is the actual picture. When an aircraft loses wing, in this case, doesn't only lose symmetry, but loses the control surfaces. Both of them make the aircraft unstable. It flips and falls like a rock. This pilot was doing air combat maneuvers with his wingman, and wingman realized what had happened. He parachuted to safety. The F-15 pilot was sitting up here, and as you know, there are no rear view mirrors in an aircraft. So he had no idea what had happened. He controlled it by seat of his pants, using engine thrust, using his afterburners, and the control surfaces he had. He basically turned the aircraft into a missile. It landed at twice the speed that it was supposed to have landed. And then the pilot looked to his right and said, "Holy cow." He couldn't believe how much damage there was. If he had known that, he would have parachuted to safety also, but he's an amazing pilot, he landed it. When it happened, the aircraft was built by McDonnell Douglas in St. Louis, now Boeing Phantom Works. So they brought the pilot, they brought the aircraft to St. Louis. It went through wind tunnel testing, and I had the privilege of being part of the team that developed a damage adaptive modeling, we call it parameter estimation, and control for this aircraft. So what we developed, and it was about 3 doctoral dissertations later, about 4.5 years later, we developed real-time, fast ways to assess what's the damage. Basically, within 3 seconds after collision, we could reconfigure the aircraft and know exactly how to control it against a broad array of failures, damages, either structural or failures, equipment failure, and reconfigure the system and control it. Every 20 milliseconds, every basically 1/5 of 1/10 of a second, we could update the parameters of the aircraft and move it to stability. This is an actual flight test at NASA Dryden in 1997 with complete hydraulic failure, similar to what you may have remembered from Sioux City, Iowa, or you may remember the more recent unfortunate tragic ending in upstate New York, that when you lose hydraulics, you lose the control surfaces. This is hydraulic failure. The pilot puts a lateral stick, blue. Our system compensates for the damage and follows on the red line. So almost precisely follows the command of the aircraft. So to share with you in a nutshell, I did this beginning in 1983, working on systems, single aircraft, squadron of aircraft. If one aircraft goes down, 2 aircraft in a squadron go down, can you keep the mission effectiveness? Then we moved on to networks. For Department of Defense, Air Mobility Command, Transportation Command, what if an airbase goes down? What if a fueling capability goes down? So doing dynamic, real-time risk assessment and also reconfiguration of these systems. Move to civilian application, intelligent transportation systems, intelligent vehicle highway systems, and then move to, I had the privilege of leading mathematics and information sciences for our nation's organization. It's a 501c3 called Electric Power Research Institute, EPRI in Palo Alto. So in that we move this whole area into large-scale, interdependent, lifeline national infrastructures. So during 1998 to 2002, funded 28 universities in the United States, 108 professors, over 240 graduate students in the area that we call complex interactive networks. How to make these large-scale coupled systems adaptive, responsive, enabling interconnection of renewable sources, other sources into them, and also understanding the dynamics between price, watts, and environmental impact. That was very successful. This is called the mother of smart grid. This was the initiative that led to smart grid and what at the time I called self-healing grid, later on became IntelliGrid and modern grid. So in a nutshell, what we do, and this is actually as human beings, we can feel this, relate to it. We have normal state. There is no disturbance. Things happen, we either go into an alert mode, precursors occur, we don't detect them, but we realize we got to do something, or sometimes they're abrupt, and we just go to the emergency mode. And then we try to restore the system. So there are principles that since the 60s we have developed handling these highly complex, highly nonlinear, and highly unpredictable. So it's an oxymoron in some way. It's a contradiction. We want to make complex systems simple. That's really the ultimate goal. But in a nutshell, we don't want to dilute it. We don't want to make these systems stupid. We want to make them simple but smart, if that makes any sense. So the idea is, how do we distribute intelligence? Where do we put them with the goals of increasing security, reliability, resilience, robustness, and efficiency? Those are the 5 goals that we go after. So since then, at EPRI, I won't talk too much about that. We had the privilege of doing it. After 9/11, I happened to be in Washington, D.C., less than a mile away from Pentagon, presenting to the White House, OSTP, and other agencies on that tragic day. When I got back to Palo Alto on Friday night, I was put in charge of all the security research and development for our nation's utilities. So we took some of this work and applied it to how can we make the role of science and technology beyond not just guards, dogs, cameras, and guns, but what can science and technology do? Dynamic risk assessment, protective reconfiguration of the system to save the system, and penetrations, for whether they are cyber communication systems or whether they are attacks on the system, to be localized. But 6.5 years ago, after that, moved to University of Minnesota. So some of the work that I will share with you has both of these. But in a nutshell, when I dig into the smart grid, before I dig into it, think about all the challenges we have when it is environmental security, national security, economic security. I know we have a cheat sheet on the screen, but when you sit back and close your eyes and think, what is at the core of all 3 challenges? What's at the nexus? Environmental, economic, national security. It's energy security. So it's when we think about our nation, America reimagined. That's at the core of one of the key areas a problem that matters for our 21st century United States. And underneath that, what pieces are there? This, at the beginning, may seem like a very forbidding view graph, but allow me to, together, let's walk through it. On your left-hand side, you're seeing all the input, all of our total energy that we use in the United States, all the input to the system. On the left-hand side is all the input. On the right-hand side is all the total system, how efficiently is this energy used. So 40% of our total energy comes from petroleum, 22.6% from natural gas, 22.8% from coal, 8% from nuclear, less than 0.06% from solar, 0.15% from wind, 0.3% geothermal, biomass is about 2.8%, hydro is about the same, 2.7%. So they go through various uses, various channels from transportation sector, and you're going to have a great presentation later on both of the areas that I'm highlighting here in this panel. What do you think is the overall end-to-end system efficiency? the way we use energy basically in the United States. 43%. Over 55% is wasted. How? I'm an engineer. I like muscle cars. The car I drive has 380 horsepower. 84. It's losing a few here. Maybe it's 380 plus a couple donkeys now. But the efficiency of that vehicle is about 14%. So from well to wheel, you get very low efficiency. What if, today you're going to hear more about transportation, what if you electrify transportation and you put electrons, you don't sweep it under the rug. We got to treat, the second message I want to share with you, we got to treat the whole system, not just a subsystem, because if you optimize subsystem, you do not take care of the whole system. We got to go from micro to macro, from local, similar to aircraft, to squadron of aircraft, to whole network, similarly for our energy. So when you look at the two biggest sources of loss, these are the gray pipelines. The largest one is coming from transportation sector, is 29.5% losses from there. Electricity, my area, is 25.5. The grid itself is, in that sense, is very efficient. That was the way it was designed, because it was more efficient for alternating current to be produced in massive amounts away from population centers, and then bring it through high voltage transmission lines into population centers. The grid loses about 7 to 9% loss. The big sources of loss are at the two ends, are at the generation side, fossil fuels being converted to electrons, and at the end use in our homes. How efficient are electric light bulbs in your homes? The amazing innovation by Edison, what do you think was the efficiency of that? 7%. It's a better source of heat, 93% heat, than illumination. Similarly, our refrigerators have gotten about 50% larger than 1970s, and they use about 1/3 of the electricity. We are improving, but we have a long way to go in end-use efficiency. LED lighting has about 12 times more efficiency than the original light bulb. So when you look at all this, these are the recommendations that on behalf of Institute of Electrical Electronics Engineers and American Society of Mechanical Engineers, Discover Magazine, and National Science Foundation, I made last week to the Congress. So number one is increasing system efficiency. Number two is building a network, because the most efficient way to capture energy and transfer that energy is not through compressed air or compressed ammonia or hydrogen. The most efficient way is through electrons. So you need to have a superhighway retrofitting the existing North American 216,000 miles of high voltage line with a system that would enable our 21st century digital society, is this part. Transforming the network, expanding the transmission, and the other part is breaking on addiction to oil, transforming transportation, but from sources that are sustainable, and basically sources that are more efficient and more secure. Finally, greening of the grid is the use of renewables together with advanced nuclear. We have 104 reactors in the nation. How many designs do you think these 104 reactors have? 104. 103 actually, to be precise. French had generation 1, generation 2, generation 3, now they're going to generation 4. From a maintenance, from a regulation point of view, it makes it a lot easier. And there is a lot more we can do in storage. If you're going to develop a system that integrates intermittent sources, such as solar, such as wind, we need to have storage, because these sources are intermittent. You need to store the energy. So everything from, you're going to hear more about it in today's presentation, but from electronically controlled flywheels to advanced battery technology to other innovations that we're going to hear more today, or during Q&A, I'll be happy to help. So to give you an idea, the gray areas is where sources of energy are. The red dots are population growth centers in our nation. The blue arrows is the direction that energy has to be captured and transported. So what do you think this gives you an insight to? This gives you insight to the superhighways that we need to retrofit our existing system with. Here it is. The maroon part, the existing North American grid, which is a marvel of engineering. It's an amazing system. National Academy of Engineering termed it as the greatest achievement of engineering in the last century. Actually, the gentleman in charge of that Blue Ribbon Commission in 2000 was Neil Armstrong. When he was selected, I thought, oh, it's man walking on the moon. It's the greatest achievement. But you know what? Without networks of electrification, we could have never walked on the moon. Without networks of electrification, everything in this room will go dark. So this network needs to be upgraded, and the backbone we need to put on top of it is the maroon part you're seeing. American Electric Power, that also operates in 11 states, has done an assessment, in addition to DOE, EPRI, other organizations, what it would take to integrate renewables, in this case wind, into the grid. Existing high voltage that they have is the green part. The orange part is what needs to be developed and retrofitted, expanded. This also will help electrification of transportation. So in a nutshell, I interviewed colleagues from Nature magazine July of last year. Their graphic artists did a fantastic job capturing the whole vision much better than I could have done. Here it is, retrofitting buildings with building integrated sources, whether they're solar panels, they're building integrated wind, storage, not necessarily compressed air, but other storage, integration of renewables, retrofitting existing infrastructure. It's about a $1 trillion system we are talking about. $1 trillion system we have invested already in the last century. But it's being operated more like a 1960s aircraft rather than a 2010 aircraft. The control system and sensing we're using for most parts of it. An ability to make it more secure. It would take about 6 areas of development for us to transform it. Real-time understanding of what's going on, integration of renewables into it, self-healing system, asset management and online monitoring, participation, intelligent devices in our home that can negotiate price, demand response, reduce emissions. This vision, Wired magazine captured what we were doing. Basically, every network, every node in the network of the future will be smart, will be eco-sensitive and adaptive and interconnected with everything else. However, this system is underfunded. Here I captured how much money goes into research and development as a percentage of net sales. Where would you expect electricity that underpins our economy and our quality of life to be? On your left-hand side, you're seeing the top 10. Engineering management services, computers, pharmaceuticals, amusement parks. From 6%, 6.2% to about 13% of net sales goes into R&D. Electricity is grouped together with gas and sanitation services, is second from the bottom. This was the data analyzed 1995 to 2000. Unfortunately, that number has dropped. The new number is, this used to be the data I shared with you, used to be 0.3% of net sales went into research and development. That has dropped to 0.17%. We are only second to pulp and paper in how much we spend. So this is an engine for economic growth, investment in this system, upbringing it to the 21st century. I have done assessment, technology assessment, policy assessment of what it would take in a risk-managed way, long-term, to make this transportation happen. Here is a snapshot of enabling parts as well as parts you build on top of the foundational part. Foundational parts are energy and power, information technologies, nano, bio, IT. On top of it, you can build, in Minnesota, medical devices are huge. Medical devices, agri-technologies, and security for us. Bigger picture, I have done assessments of it for developing parts of the world, Egypt, Taiwan, and for advanced societies, European societies, China, India, as well as United States and Canada. How do we expand, if you will, our economic development in a way that it is based on science and technology, it is secure, it is resilient to disturbances, and it is sustainable? So in a nutshell, these are the areas, with the help from my colleague Kirk Froggatt at the University of Minnesota, the areas that we have assessed and we are looking even more into in this area. Kirk calls it focus. basically, and he calls the whole thing about face conversation. Having focus, having alignment, building networks of collaboration such as what you're doing, and execution. So to conclude, we have to transform this infrastructure from what was built to provide electrons for lights and refrigeration to one that energizes a networked digital economy. And to do this, I'm asking for your leadership. It takes leadership to transform this and commitment to make it happen. So the challenge is, will this infrastructure be left as a relic of the last century, or be the energizing, enabling infrastructure for a digital society in this century? Especially when you think globally, there are 1.2 billion people in the world with no access to electricity. 1.4 billion people have inadequate access. They have outages of 4 hours or longer per day. And most of their challenges boil down to what we, trilemma of sustainability: population, pollution, poverty. And that is the main challenge for our 21st century, and a challenge that matters for us in America, to think of it as a systematic way and transform the infrastructure into smaller, smarter, more resilient, more secure, and sustainable system. Thank you.
That's great.